Might as well get on with tonight's talk. You ready to go, Steve? Okay, we're going to just have a bit of a discussion about star catalogues, naming conventions, deep skies catalogues. Some of them are a bit confusing, but hopefully we'll be able to demystify some of it. So the first thing I want to talk about, though, before getting on to that, is coordinates. And this is because one of the key things, or a catalogue isn't really much use unless you can locate things on the sky that it's talking about, stars and so on. So this is one of the key things to understand. And astronomical catalogues refer to a position of objects in right ascension and declination. The declination's pretty easy to understand because it's just the Earth's latitude projected onto the sky. So if you're sitting on the equator, the celestial equator is directly above your head, and that's declination 0. If you're at the pole, either pole, it's either plus 90 degrees for the North Pole or minus 90 overhead if you're at the South Pole. So it's pretty straightforward. Whatever latitude you're at, directly overhead is basically the declination of your latitude. So the other one is the equivalent to longitude, and there's two differences. Instead of measuring in degrees, like from the Greenwich or the prime meridian that universal time is worked out from, instead of measuring that in degrees east or west, in the sky we measure in time. And this is because it's convenient, because your telescope is pointing, say, at a fixed point in the sky. As things are moving past, you can measure it in time more conveniently than an angle. So if you're 2 hours away from something passing in front of your telescope, but that leaves the issue of what's the origin of the coordinates. You haven't got a place on Earth you can say, oh, we'll arbitrarily set it here. So you need to set somewhere in the sky that's going to be the 0 position for right ascension. And the way that's done is they use the two great circles. The one is the celestial equator, and the other one is what's called the ecliptic, which is the path of the sun through the course of the year. It also defines the plane of the Earth's orbit, the ecliptic, and it's also where eclipses occur. So that if the moon is crossing the ecliptic, either at the same position as the sun, you get solar eclipse. If it's on the opposite side of the Earth to the sun, you get a lunar eclipse. Again, that doesn't happen every month because the moon's orbit is also at a little tilt. So you have to get the conditions just right for that to happen. So the ecliptic is tilted at about 23 degrees to the celestial equator. You've probably heard of the tilt of the Earth's axis, or that's exactly what we're talking about. So, the two planes are tilted, and where they cross are called the equinoxes. So there's the vernal equinox and the autumnal equinox, but it's oriented towards the northern hemisphere. So the vernal equinox is actually our autumn equinox, and it's the spring equinox for the northern hemisphere. So that crossing point where the two lines cross is where the sun is at the equinoxes, and it's also the 0 times 0 for the right ascension. There's a bit of a complication because the Earth wobbles around on its rotational axis once every 26,000 years. So the coordinates actually change slowly over time, which makes things a bit of a nuisance. So what you have to do when you say the coordinate of a star is such and such, you have to specify what the date of that position was. And then there's a simple calculation to what they call precess the coordinates to the current date, and that's what all of your planetarium programs like Stellarium, Sky Safari, all those things have to do, because they'll have a catalogue with the coordinates based on a certain date, and then they have to bring them to the current date that you're observing. And of course you can set the dates in those programs back in the past or the future, so it has to do the calculations to show you how the positions of the stars. So anyway, that's probably enough on coordinates. Another type of coordinate we use is called the hour angle, and this is useful for the local observer because it tells you where the object is in the sky at the moment, and again it's in time, but it tells you how far east or west of the meridian going over your head is. So if the hour angle is 3 hours, it means that the object is 3 hours past the meridian. If it's 21 hours, then you know that it's going to cross the meridian in 3 hours' time. So that's your local hour angle, and you probably see that in any of these programs, as well as the right ascension and declination. They'll tell you the hour angle of the object. So that hour angle is specific to your location, but it's quite a useful thing to know. But if you're observing, think, oh, okay, that object is going to be crossing right overhead in 3 hours or whatever it might be. So in terms of catalogues now, probably the most well-known early catalogue was one compiled by the Greek astronomer Hipparchus, and he had about, I think his catalogue had about 1,000 stars in there. So we will, oh, that slide is actually out of place, sorry about that. Actually, before we get on to, I have to skip this, so before we get on to catalogues of stars, we need to start off with the way the sky is divided up into constellations. Historically, they're based on cultural things like patterns in the sky, like we have the local Maori people have their star patterns. Every culture has this, but the IAU based their system on what's basically the Greek and Roman system that goes back to Ptolemy in about when was it, 3rd century AD. And so in the Johann Bayer wrote a book called Uranometria, and it was basically all of these plates which have artwork like you see here. That's the constellation Orion, and they actually are quite interesting. But he tries to show how bright the stars are by their size, and he also gives them an identification instead of just a name for a star. He came up with this idea of ordering stars by their brightness. So this is where you have things like Alpha Centauri, Alpha Orionis, Beta Orionis. So it just uses the Greek alphabet to order things in brightness. There's a few discrepancies where like Beta is occasionally brighter than Alpha and things like that, possibly because they misjudged it. But these are quite nice plates, and Uranometria has one of these plates for each constellation in the sky. And then the poor old southern hemisphere only gets one plate because at the time this was being compiled, they only had limited knowledge of the southern hemisphere. So this arrangement, and there's fanciful creatures and so on that they just assigned to the constellations in the south. And these didn't take notice of any indigenous knowledge at all. They came mostly from Dutch navigators and I think a French pastor who was located in South Africa, Abbé Louis de Cael. And so that's where this particular arrangement came from. So when the IAU was established, they decided, it's the International Astronomical Union, it's effectively an organisation of all the professional astronomers in the world, and they came up with a scheme of, we divide the sky into 88 constellations, and they tried to keep with the Greek and Roman traditional ones. Obviously, for the Southern Hemisphere, they had to add new ones, and they defined the boundaries in a way where the boundaries are lines of constant right ascension or declination. And this scheme was adopted back in 1930, And the coordinates of the boundaries were based, as I mentioned before, because of precession, you have to specify a date. They were based on the year 1875. So that was the coordinates as determined in that date and then precessed. So that's what we ended up with. And because of this, some of the boundaries look kind of weird. You see a whole lot of short line segments. So this is the official, showing the official boundary of the constellation Orion. But it does mean that you can say, yes, this star is part of Orion or it's not, based on the boundaries. Whereas if you're just using a traditional thing, well, if it's sort of over to the side a bit, you're not sure which constellation it's in. So it does sort of make it systematic. And this table here is showing you the names of all the constellations, and they all have a 3-letter code, which you can learn if you want to. I can't rattle off all 88, that's for sure. The other slightly unusual thing you may have come across is that when you refer to a star that belongs to a constellation, they use the genitive form of the constellation name. So we don't say Alpha Orion, we say Alpha Orionis. So that's in Latin, they use the Latin genitive to refer to the star. You can sort of think of it means of Orion, Alpha of Orion, if you like, telling you which constellation the star belongs to. Sort of like a possessive term. Right, catalogues, general things that you might have in a star catalogue. One thing is a proper name. Obviously we know of billions of stars these days, so you can't really give proper names to them all. So there's only a limited number of stars that are given proper names, like Rigel, Betelgeuse, those kind of things. And it was actually a working committee of the IAU set up to have official star names. So I think there's 227 that are officially named nowadays. And then you've got an ID, and that will, it talks about, I mentioned the Bayer Uranometria scheme, which used the Greek letters, and there's a Flamsteed system which just numbered the stars within the constellation. And obviously for actual location you need something a bit better than that, so you have the position and right ascension and declination plus the date that applies to, so you can do the precession calculations. Generally that will be constant through the catalogue, so they say the catalogue is valid for some epoch, and then you need to precess all the coordinates to get to the current date. Another obvious thing is the brightness of the stars. There's several different ways you can measure brightness, but a common one is visual magnitude, and I'll explain a bit more about that later. Parallax, which is basically telling you the distance of the star from the sun, the Earth. You've got spectral type, lots of other things that you could put in there. Proper motion. If you're not familiar with what proper motion is that stars are not only moving relative to because of the change in the coordinate system, but they actually do move on the sky. And for the nearby ones, it's measurable even probably by amateurs without waiting too long. Like stars like Alpha Centauri actually move relative to the other stars quite quickly because they're nearby. Okay, so that's the kind of information that a catalogue is likely to have. Oh yeah, a bit on the proper names. The names that we have are mostly derived from Arabic and Latin names for the IAUs. Yeah, and we've got 227 approved official star names. And you can see that website link there tells you how to find the IAU information on star names. And for visual magnitude, the named stars range from Sirius, which is Vmag minus 1.44, and I'll get to explain a bit more about visual magnitude as we go along. But you notice that the visual magnitude of Proxima Centauri is a named star, but it's magnitude 11. You can't see it with the naked eye. In fact, you need a fairly decent telescope to see down to magnitude 11. So you wonder, well, why has that been given a name? Well, it's just purely because it's the closest star to our solar system. Okay, mentioned the way the Bayer designation worked, brightness order within constellation by Greek letter, and Flamsteed system, which was just numbered in right ascension order within a constellation. For example, 22 Eridani. And this is one of these genitives, so the constellation is Eridanus, but we refer to stars as Alpha Eridani, 22 Eridani, that kind of thing. Okay, so I've we've probably already talked a bit about this, declination and right ascension, and the origin being the point at which the sun crosses the celestial equator from south to north, known as the vernal equinox. Also, if you hear the term the first point of Aries, that's what it's talking about. And the position is no longer in Aries, it's actually in Pisces, and that's because of precession since they came up with this term. And does anyone know that it crosses into Aquarius in the near future? Does anyone know exactly when? That's what this age of Aquarius is all about, if you've heard that song. Okay. So visual magnitude brightness is actually based on Hipparchus's star ranking system. So obviously they couldn't accurately measure star brightness back in those days, so you just had to estimate it by looking at the stars, and he gave them a ranking, the brightest stars being first magnitude, and then the ones that you could only just barely see, sixth magnitude. So that's where the origin of the visual magnitude system. But obviously with a telescope, for example, it shows there down to magnitude 32, which is what the Hubble Space Telescope can do with a deep exposure. So that's interesting, but then you can have things that are much brighter than stars. So obviously the sun is a star, obviously, but because it's so close, it's very much brighter than first magnitude. And in fact, if you extend this system, it turns out the sun is around magnitude, well, it's actually brighter than minus 26. So basically, things get brighter, they become more and more negative on this system. And the way it works is that, in scientific terms, or in the modern definition, is that every 5 magnitudes difference is 100-fold difference in brightness. And this is just an arbitrary thing. It was done to approximate Hipparchus's system. So, it basically means that a first magnitude star is 100 times brighter than a 6th magnitude star. And you can do the calculation. The difference of 1 magnitude is the 5th root of 100, or 2.512. So a first magnitude star is 2.512 brighter than a 2nd magnitude star. And of the stars, other than the sun, the brightest is currently Sirius at minus 1.46. One interesting thing is that to calibrate this, you need some kind of reference. And originally, when this Pogson came up with a scheme, they used Polaris as the standard, and they just said, right, we'll decide that Polaris is magnitude 2. But the problem is it's a variable star, so it's not very good as a standard. So they then went to Vega. Vega even has a small variability as well. So now it's just they measure in absolute flux terms. as measured on a photo multiplier in the old days, or now on a CCD camera. Okay, the other thing about brightness, we've been talking about visual magnitude, but this is apparent magnitude. In other words, how bright it looks to us. It doesn't take into account the distance. So obviously something really bright and really far away can look faint. So basically follows the inverse square law. So what we want to do is have a measure of brightness that tells you how actually bright the star is. And so you use a trick to do this. You pretend that the star is at a fixed distance. And for this purpose, we use a distance of 10 parsecs, or 32.6 light years. So if you see a measurement for the absolute magnitude of a star, it's basically how bright it would appear to be if it was at a fixed distance of 10 parsecs. So that basically puts the comparison of brightness between stars, so you know which are the really intrinsically bright ones by basically calculating how bright they would be at a fixed distance. So you'll find absolute magnitude, and that's the difference between absolute and apparent magnitude. These are both visual magnitudes, I might point out. There are other magnitudes that are used for various scientific purposes, like you might be interested in particular wavelengths of light or band passes. Another important thing with stars is we have what's called the spectral class. And you see that it's got a funny system where we have the letters O, B, A, F, G, M, K, M rather. So this system came from Harvard University with a group of women who were called the Harvard calculators. And they got all of these spectrographic plates. This was in the early days of photography and spectrographs. And I think Annie Cannon was the main leader of these people. And they tried to work out, looking at the spectral lines, how they could catalogue different kinds of stars based on their spectral lines. And I think they did start off with A, B, C, D, but they soon realised that there was a whole lot of confusing things going on. And by the time they sorted it out, this is what they ended up with. So basically the hottest stars are on the left, the O stars, and the M stars on that scheme are the coolest. And then you can further subdivide it from O to 9, basically, because you can actually get the brightness. This is measuring, what did I say, luminosity. Its spectral class is really related to temperature. So, it's divided up into 10 for each letter, from the hottest to the coolest within that class. And then there are other different types. You'll see V means main sequence. And for example, the Sun is a main sequence star and is classified as G2V. So it's spectral class G, G2 actually, and then V meaning main sequence. And the table you see down below there shows you what those letters mean. They're what are called luminosity class. And they go from 0 down to V, actually the Latin numbers. It gives you a description of what those type of stars are. For example, the Sun is classed as the main sequence dwarf, and then these other ones, you've got giants, bright giants, subgiants, and so on. Don't worry too much. Okay, what sort of catalogues do we come across? Fairly common one for amateurs, which is really good for visual or binocular observing, is the Yale Bright Star Catalogue. And the catalogue identification starts with HR, so and this covers all the stars in the sky down to magnitude 6.5. So it's basically all the stars you can see visually without optical aid. Some other ones, a bit of a, you won't find it so commonly these days, the Bonner-Durchmusterung, which is basically this was a catalogue of stars going down to 10th magnitude, so you need a telescope to see most of them. Obviously, the fainter you go, the more stars there are. And so they basically divided a catalogue up into zones. You may come across this, it's not so common these days, as the BD designation. And orders by RA within a zone of declination is the way the scheme works. Probably one of the fairly important ones, the Henry Draper catalogue. I mentioned before the Harvard University. Basically, Henry Draper was an amateur astronomer, and after he died, his widow actually paid to have all of that work done at Harvard University that Annie Cannon and what was her name, and Miss Fleming, what was her first name? Can anyone remember? Yeah, there were a number of women who actually worked on this at Harvard University, and so basically this Henry Draper catalogue is effectively the result of their work, and the Harvard classification scheme for stellar spectra. You've got the SAO, you see that quite often, Smithsonian Astrophysical Observatory. This is a positional catalogue is what its primary focus is, astrometry. And similar, the Hipparcos high precision parallax collecting satellite, that was a satellite put up by the European Space Agency. And because they were above the atmosphere, it was easier to get accurate positions of stars. From the Earth, it's difficult because of the atmosphere distorting the basically twinkle, gives you a bit of distortion. It's hard to actually get accurate star position measurements from the surface of the Earth. And until recent times, parallax information for the majority of stars was the best we had. It was possible, like the Hubble Space Telescope did a few specific stars, but you can't survey the whole sky with the Hubble Space Telescope, but they did some calibration against the Hipparcos satellite with a few selected stars. And then you've got the US Naval Observatory catalogues, Tycho 2, and USNO catalogues, and also the UCAC series. They all put out by the US Naval Observatory. And of course they're interested in this for navigational reasons. And then the current catalogue of the day, I guess, which is still being compiled, is the Gaia catalogue. And this is another satellite that ESA put into orbit, but it's much higher precision than Hipparcos. And I think its catalogue, I think Hipparcos had a few thousand stars in its catalogue. Gaia is going to have more than 1 billion stars, and its astrometry is amazing. They can get down to something like 10 microarc seconds in their positions. And each data release they do gets more and more accurate. And I think I read the final version of the catalogue won't be available until 2030. And that'll be data release 5, it's going to be called. The satellite is still operating, although I did hear it recently had a problem. A micrometeor hit it and damaged a sun shield. So they're unfortunately getting a bit of stray light getting to the focal plane now from damage. And luckily it hasn't actually damaged the electronics or the mirrors, but it actually basically poked a hole in the sun shield. And so that's causing them a few problems. Just as an illustration of this Gaia catalogue, you might think, oh, that's a photograph. But what it actually is basically a plot of all the star positions out of the Gaia DR2 catalogue. So it's pretty amazing. You can actually get what almost looks like a picture just by plotting all the individual stars on a chart. So that's an all sky one. You can see the Magellanic Clouds show up quite prominently there. Now, I don't know if this is going to work. Oh.
Is the next one going to be the Nancy Roman? Is it going to be the next catalogue one?
Sorry?
Next satellite that goes up? No, that's the
I don't know there's any immediate plans for sort of like a Gaia Mark II. There's other ones being sent out, like an updated or the next thing that'll replace the Webb telescope. But the Webb and those kind of telescopes are not doing what Gaia's doing, trying to catalogue the entire sky. They're looking at specific parts of the sky, at interesting objects, I guess. Unfortunately, I don't know why, but this isn't working. I can tell you what I was going to show you. It was another bit of info. You can look it up on YouTube. Not sure why it isn't working, because it did. Yeah. What it is basically a colour magnitude diagram from the Gaia satellite. So if you're not familiar with what those are, you plot the temperature or an analogue for the temperature. What they do for Gaia is it's got different filters, and you say subtract the brightness difference between a filter at the blue end and another filter at the red end, or green, or whatever. You can use any two colours actually, and the difference gives you actually an estimate of temperature of the star. And the other thing is the absolute magnitude, which you can now, because you've got really accurate parallax, you can get that from the Gaia database. But Gaia actually goes back and observes these stars over and over again. I think it's up to about 70 times for most stars now. So it can actually see that things have changed between each measurement. And what's changing is the variable star's brightness. So what this showed was a colour magnitude diagram, but it was plotting the changes, and you could see all the Cepheid variables and other variables that were within the sort of the time cadence that it could pick up. You can see them as they actually move around on the colour magnitude diagram. I'm used to sort of thinking about these things as just fixed, but in fact, because they're variable stars, they're not fixed in a certain position. They move around over relatively short time spans of days to months. I'm sorry, for some reason that isn't working. Anyway. Oh, this is just star identifiers, and this is where you can get really confused. These are probably not even all of the catalogues, and you might think, well, what the heck is all this about? And it turns out that this is actually the star Aldebaran. So, if you might notice right in the middle there. So how the heck do you deal with this if you come across a star catalogue and you're not really sure? What's really helpful is down the bottom here, the site simbad.ustrasbourg.fr. If you just search for Simbad star info, it'll bring it up on Google. And this university have been very kind, and they've got a database of all these. So you type in any one of those and it will tell you all the other catalogues that star is in, proper names and any other information. So it's quite a handy resource.
So each of those lines is a different...
Oh, they're all...
The same one, okay.
Yeah, different catalogues. So there's more than one on each line. So there's probably, I don't know, about 30 or 40 catalogues on there.
Did you say 53?
Sorry? Yeah, that's right up the top. It actually tells you how many are listed there. So there's 53 different catalogues, all a proper name for Aldebaran. So I should have left Aldebaran out and asked if anyone could identify what this was.
Nope.
Okay. So talked about variable stars. So they have a different naming scheme where they use a capital letter, Roman letter, and then when they run out of capital letters within a constellation, they start doubling them up. So, for example, you've probably heard of things like RR Lyrae stars. Well, that's because the star RR Lyrae is the sort of the typical type of that type of variable. So it was identified in the constellation Lyra, and so on. When they run out of double letters, they then give up and then just go V followed by a number. So you see a number of different designations for variable stars. Some fairly well-known ones in the southern hemisphere, like R Centauri, T Pyxidus. It's not so common now, but this was a big activity of amateurs for basically measuring variable stars, usually just visually. And if you haven't heard of him, there was a fairly famous New Zealand amateur astronomer, late Albert Jones, who lived in Nelson. He compiled 500,000 observations of variable stars in his lifetime that he submitted to the international body. So it's pretty impressive. He also discovered at least one comet. It was named after him. I think he jointly discovered the comet. He was also one of the first to discover supernova in 1987A. Okay. Right, that's enough of stars. We'll better move on to the deep sky. So these are obviously non-stellar objects, usually. There's kind of a bit of a caveat to that I'll explain a bit later. Often for these, if you're looking at star charts for these, there's a bunch of symbols along the bottom there so you can recognise what type of object is being shown on a chart, and most of the software uses pretty much the same convention, maybe not the colours or what they're filled with, but like an oval like that for an ellipse type shape for a galaxy, a dotted line and a circle for an open star cluster, closed line with a cross is your globular clusters, and then the sort of like the cross on the outside of a circle indicates a planetary nebula. If you're not sure what that is, that's a type of nebula that's basically the atmosphere that's being thrown off from a star at the end of its life, leaving a white dwarf core. And they don't last very long because obviously the nebula is gradually dissipating into space, and the sun will end up like that one day. It will be observed by alien astronomers as a planetary nebula, wondering whether...
Because it's planetary, but it's not.
It was called planetary because they're often round and relatively look a little bit like planets. And some of them have got names like the Ghost of Jupiter, because it looks like a fainter version of Jupiter. There's a Ghost of Saturn as well. I think the name was made up by the Herschels, is where it comes from. The term planetary nebula. And then you've got your bright nebula, which is your emission nebulas, like the Great Nebula and Orion, that kind of thing, which are generally irregular in shape. Solid dot for a star, and often they will vary the size to tell you an estimate of how bright it is. Obviously, it'll be a white dot if you're looking at a planetarium program on a dark background. And then an open circle like that for a variable star is quite often used. So if you're looking at star charts or planetarium programs, you see these symbols, it gives you an indication of what the object is. Okay, probably the most well-known one is what's called the Messier Catalogue, which was compiled back in the 18th century by these comet hunters, mainly Charles Messier, but he had a lot of assistance from Pierre Machin. A lot of the observations was done from Paris. There's about a bit over 100 objects, something like 110, I think. And they, it's pretty amazing to think these days. You couldn't do it from Paris now, or any city in the world, because of the light pollution. because they didn't have big telescopes really, and a lot of these objects you wouldn't be able to see from here just because of the light pollution. Even with the Zeiss, they just get washed out by the city sky. So the main reason that they did these is they weren't actually interested in these objects. They catalogued them so they wouldn't be mistaken for comets, because that's what their primary interest was, discovering comets. So they'd say, oh, is that a comet? Oh no, it's in the catalogue. It's basically a fuzzy blob that's always there. Okay. In the northern hemisphere, they have what's called a marathon, where certain times a year where you can actually see every one of them during the course of a night. So you have to start at sunset and work your way through to the dawn before you can see them all in one night. But it is possible, not so from down here, unfortunately. So if you see the term marathon, that's what they're talking about. But as it says at the bottom there, you do require a rural sky to have any chance, or preferably a truly dark sky. Okay, I found this on the internet. Somebody had done a little project to actually photograph every Messier object and put it on this poster. So that's them. Okay, a little bit similar to the Messier catalogue, but it's called the Caldwell catalogue, where this is the late Sir Patrick Moore decided that, well, Messier missed a few things, and there's also a lot of things in the south that he couldn't see. So he came up with this, basically, I guess you could call it an extension to the Messier catalogue called the Caldwell catalogue. And sometimes there's multiple names for these objects. As you see here, we've got Caldwell 106, which has also got a star catalogue name, 47 Tucanae. You might think, well, that's a bit strange. It's because this one is visible to the naked eye, but it was catalogued as a star. And it's also known as NGC 104, which is a very nice southern globular cluster, which many of you have probably seen. Another one, not so well known, but is the Bennett catalogue. Jack Bennett compiled this as basically a full catalogue of Messier type objects, but only for the southern hemisphere. So you might come across that. One of the more important ones is the new General Catalogue of Nebulae and Stars, which was new in 1888. This was compiled by John Dreyer, and it was before the use of photography, so it's all done sometimes with quite large telescopes, going back to those days. Majority of the objects were basically the Herschel family. William Herschel built what was the largest telescope of the day back in those times, an 18-inch Newtonian type telescope. And Caroline was William's sister and John was William's son. John basically continued. John was a scientist in a lot of other areas in his own right, but he did continue his father's work in South Africa. He went to Cape Town to basically catalogue all the faint fuzzies of the southern hemisphere, and basically their work is the basis of the new general catalogue, but a lot of other stuff as well. There is a bit of an issue with the way they did these catalogues. Is the catalogue numbers are ordered by right ascension. So if you have NGC 104 and NGC 105 and you find another object that's between those two in right ascension, you can't put it in the catalogue. They didn't allow for fractional catalogue numbers. So what they ended up doing is they started discovering a lot more things with photography. So they basically created two new catalogues, Index Catalogue 1 and Index Catalogue 2. So if you see on a star chart it says IC followed by a number, that means that it's in the index catalogue, which is basically an extension to the NGC catalogue. So this is pretty important because it covers virtually all the galaxies and nebula that an amateur would ever be looking at, probably, because it goes down to quite faint stuff. Actually, I forgot the point I was going to make. It just came back to me. When we were talking about Messier objects being deep sky, well, some of them are actually not single stars, but clusters of stars. So when I said non-stellar, well, maybe it's a bit arguable as to whether a star cluster really is a group of stellar objects. But because they kind of look a bit like a fuzzy object, that's how they get catalogued as being deep sky rather than stellar, I guess. When you get into galaxies a bit more, there's the principal galactic catalogue, principal catalogue of galaxies. This is obviously a much more recent one, and there's you've got 131,601 galaxies. Obviously, a lot more galaxies are known than this, but you're starting to get into really faint stuff when you get outside of this. And of course, a lot of galaxies are just not catalogued at all. You might also come across a list of objects called the Malott catalogue, and these are basically star clusters, not nebulae. And there's also Barnard's catalogue, which is a bit different. Instead of being bright nebula, they're dark nebula. So, for example, in the Milky Way, you see a lot of dark areas. So all of these have been catalogued by Barnard, and 370 different ones. Surprisingly, the Coalsack Nebula and the Southern Cross. If you go to a really dark, moonless night, well away from the city, and look at the Southern Cross, the Coalsack Nebula, as it's called, is quite obvious. See this dark patch beside the Southern Cross. And of course, these are not areas where there are no stars, areas of dust and gas that's blocking out the background stars. Okay, that's enough for the celestial type objects.
Bill, just one quick question.
Yeah.
James Webb's finding hundreds of thousands of different galaxies every week. Do they get added to a catalogue?
I don't know if they're doing that. They possibly have their own database, but I don't know if there's any published catalogue. Does anyone know?
Bill,
Yep.
is there anything being done to unify all catalogues?
Not really.
It's an ownership issue, isn't it?
It's something like Gaia, which is almost everything.
Well, yeah, but Gaia specifically stars. Yeah. Yeah. Oh, well, even some of the Magellanic Clouds as well. Do you know, Grant, if there's ever been talked about having a unified star catalogue?
No, but I would just say that there's some modern catalogues that we replace all the old ones. So yes, some of these stars have multiple names. So somebody working might go back to the historical name with the publishing paper, because the computer will tell you what all the other catalogue entries are.
To deal with redundancy.
Like ours, of course.
Yeah.
People publish their papers in Victoria, not by a sub-catalogue name.
Yeah, weirdly, that particular star was given a proper name. Everyone just has always called it Alpha Centauri, and then suddenly it became Rigel Kentaurus. And apparently this is a name that navigators used, and so they adopted it as an official name for the star. But everyone still says Alpha Centauri. So, and a lot of, I didn't mention it, but a lot of those deep sky nebula, you have the catalogue names like Messier this or NGC that, but quite a lot of the popular ones have got just made up names. Like you hear the Bubble Nebula, or I mentioned before the Saturn Nebula, Ghost of Jupiter, all those kinds of things. there's no particular rule, they just get, because of common use. Yeah.
What about binary stars? Are they always...
That's the tourism binary.
There is a convention for that. They normally say when it's a multiple system like that, they'll say A, B, C for each component. Yeah, so you've got Alpha Centauri A, Alpha Centauri B. It's generally the way they do that. Obviously, Proxima Centauri is an exception because it has its own proper name, and it's purely because it's just Earth-centric, being the closest to us. So there's a scheme for comets and asteroids. So comets were given names in the past, like the Great Comet of 1680 or whatever, because it was a particularly impressive comet. Halley's Comet. Now that comet got named after Halley, not because he discovered it, but because he applied Newton's laws of motion, planetary motion, and predicted its return. And sure enough, it was after his death the return was seen, so they duly named the comet in his honour. And in fact, they do have a convention now where if you are the discoverer of a comet, you get it named after you. Sometimes if it's co-discovered, they will give it a double name. So the naming convention, like you see 1P, it means that this was the first periodic comet discovered. So after that you'll have 2P and so on. Periodic means that it comes back. You also get non-periodic comets because either their periods are incredibly long and don't know whether they're really going to come back or not. Like they could have a period of 1 million years. They've never been seen before, and nobody's going to feasibly remember in 1 million years' time that comet.
Particularly when a lot of them are discovered by a certain observation, like solar, there's a huge harvest of those.
Yeah, that's right.
You will get interstellar comets. So
Yes, yeah. Yeah, that's right. I've got a mention about those a bit further on. And an example was you have a general comet will be C for comet, pretty uninspiringly, followed by the year, and then you have this letter code, a letter and a number, and that tells you the half month of the discovery and the number within that half month. So, for example, the second half of the month of February would get the letter D assigned to it. And this comet that some of us may have, somebody remember seeing this particular comet, it was quite impressive. Comet C 2006 P1 McNaught. It was, the tail was obvious to the naked eye in the twilight before it had got really dark in the southern hemisphere. Does anyone remember his first name? He was an Australian amateur astronomer. Can anyone remember McNaught's first name? He discovered a few comets actually. Colin, was it? McNaught? Yeah. So we haven't had a southern hemisphere comet as good as that since, so we're eagerly awaiting. Oh, Robert McNaught. Oh, okay, thanks. Okay, asteroids, they're given a provisional year and a similar half month and letter order within the month, not a number order like the comets. But once they've had enough observations to get a confirmed orbit, they may or may not be named. You can't, if you discover one, you can't have it named after you, but you can suggest a name, and the IAU may or may not accept your name. So in the case of, I guess the first first asteroid discovered was Ceres, so it's called 1 Ceres, although this is now regarded as a dwarf planet. rather than an asteroid. So that's sort of blowing that out of the water a bit. And then I've listed some here that were found in the region. 19620 Auckland, 23966 Maungakea, 23990 Springsteen were all discovered here at the Stardome by, I think, Ian Griffin, who used to be director here, must be 15 years ago or more?
He started here in 1998 and he's here till about 2000.
Oh, he was here for just 2 or 3 years, that's right, yeah. But the other one was actually a society member, 386622 New Zealand, was discovered by Jenny McCormick at her observatory home observatory out at Farm Cove. I don't know that any members have ever discovered a comet, so we haven't had that on yet. It's quite difficult for amateurs nowadays when you've got all of these electronic survey scopes scouring the sky for things. Well, yeah. Yeah. Okay, Grant already mentioned this, is that we now have a category of interstellar objects. These two weren't actually comets, but they were basically in hyperbolic orbits, and they were travelling so fast they can't possibly have been bound to the solar system in any way. So they were picked up. In fact, these were discovered by amateurs, and what they did is a trick by observing as early into the twilight as they could, because the big survey scopes can't look at that part of the sky because it's too bright. So these two different people use that kind of trick to find them. So the designation for this is just a number, and then the letter I for interstellar, and then you see the first one was, I believe, a Hawaiian name, or Muamua. Does anyone know? Something like a distant visitor? Or, yeah, that's right, yeah. And then the other one was named after the discoverer, Mr. Borisov. So, yeah, I'm sure more of these will be discovered as time goes on, especially once the Vera Rubin Observatory is up and running, because they're going to be surveying the entire southern sky, or everything they can see from the location in Chile every 4 nights. So it's pretty unlikely they'll miss any of this stuff, except that there's so much data coming from this thing. They've got to have enough computer power to sift through it all. So that's going to be the problem with it. So I think we're done. Any other questions on names, catalogues, or similar topics? Oh, yeah. So which catalogue? Oh, yeah, they do have specific. Yeah, they have really strange-looking catalogue numbers. You'll see they. Yeah, so I can't remember what it's called, but there will be a catalogue of pulsars. Yeah. Yeah. Yeah, I guess when they were operating the Warkworth radio telescope, were they observing pulsars there at times? Oh, okay. Oh, okay, no good for your receiver out there. Okay, well, thanks for coming along. Not very pleasant weather tonight, but